Okay, so let's talk about the first hands-on where you do this in Python. Now, you can use in principle any Python environment. In practice, some people have trouble setting up the requirements for Python and such. So what I like to use is this cloud Python environment. If you have, just log in with a Google account, and you can have a free Python environment called Google Colab, which is fantastic, and it's very powerful. And this way, all the students need is anything that can reach the internet, like an iPad or anything. A Chromebook would work. So you make a new notebook and you get a Python environment. You can just start writing code in here, and it even has an AI to try to write code for you, which I haven't played with much. But anyway, you can now execute code in the second window, and everybody is using a nice modern environment, and it's pretty powerful too. You can even get some access to a GPU, a graphics processing unit, to make your code run faster. Although for most of what we're doing here, the projects are simple enough that you don't need that. So we're going to import TensorFlow and print out the version. TensorFlow is a library that we're going to use for machine learning. And I was going to paste. I think I have to use the keyboard to paste. There we are. Says it's just going to import TensorFlow and print what version it got. When you run code, it tells you what's going on down here, and it tells you how long it ran. It run for 3 seconds, 4 seconds, 5 seconds, and so on. It's basically allocated a little virtual machine to me. Okay, so it's version 2.15.0 of this thing. So that's working. So now let's understand what a machine learning project is. If you have a series of numbers, like your x goes -1, up by 1, and y goes up 2, the first thing you notice, this is the way normal science always works. You would measure something, like pressure of something as a function of temperature, and then you would try to deduce the pattern. So I would see, well, when x goes up, y goes up. And if I look at it more closely, when x goes up by 1, y goes up by 2. So pretty soon I can figure out the relation is y equals 2x minus 1. And if I wanted to do it on a computer, I would include a command that did this in the computer, in Python or whatever language I'm writing it in. That's the old-fashioned technique where the human applies the intelligence. What I want is, I want the machine to figure out the pattern without me telling it the pattern. This is machine learning, so it doesn't take very much code. Just about 8 or 10 lines of code is all you need. I can add another block here and paste it in. And what happens is it's going to import NumPy, which handles numbers in Python, and TensorFlow, and it's going to import some machine learning model. These make neurons. Now, a neuron is just a data structure that has a value, and it takes inputs from the layer above it, and it has adjustable parameters, and it's just a linear combination of all the data points above it. So there's a slope and intercept for each neuron above it. So here, it's going to make a single neuron. Just one neuron is the model here. So you have, you feed in x, and it's going to it has 2 parameters, a slope and an intercept. So it's going to calculate y equals mx plus c. And it's going to hopefully try to figure out that the best value of m is 2 and the best value of c is -1. And it's going to do that by calculating the error. So it's going to start with random values for the parameters, predict all the data points, and then add up the square of the error. And it's going to decrease that square. So we'll see it go here. If I run this, it defines a model, and now it does 500 epochs of calculations. So let me get to the start. And it started with random numbers. The loss was 0.5. That is the error. That is how much it missed the data points by. Now, what you can do, that's something used in machine learning and a lot of physics and stuff, is if you have a complicated function, if you make a small step, the function is approximately linear. So you can figure out, by doing partial derivatives, what direction you should change the parameters in to make the error smaller. And so you take a little step in that direction, and you just do that over and over. So it took a little step and got the error from 0.59 down to 0.57. The next step took it down to 0.56, and so on. And so you just do a lot of little steps, and eventually you hit the bottom where it isn't changing much anymore. So you see it got down to 10 to the -4, 10 to the -5. So the error is effectively 0. After 500 epochs, it got there. Now, in my code here, I had it print out the prediction for 10. And since the pattern is 2x minus 1, the right answer for 10 is 19. And as you can see, it got 18.98, so it got pretty close to 10. Now we might want to see the actual parameters it put out, so we can do it again and print out the actual weights here. Get weights. The weights are the parameters, in this case, just the slope and intercept. So I'll run this one again and print out, after it does 500 epochs, which are, just steps, little steps of gradient descent, this is called. Then here's what I learned. The parameter that should have been 2 was 1.99. The parameter that should have been -1 is minus 0.98. So it's very good. It's getting within 1% of the right answers. So that's fine. Now, this is not too hard to believe because it had 6 or 7 points and they were exactly perfect. So that's not very challenging. So let's give it a more challenging problem. Let's add some error. So if I go back up to the code here, there, I can put in different y values here, and I'll just comment out the line before it, which is not really necessary, but anyway, it makes me feel better. And you can see I just modified these y values a little bit, just so it has some noise. Less perfect data. So we'll let it run. And now notice the loss starts out much bigger. The loss was 0.5 before. Now it started at 12, but it's going down really fast. So as it gets down to 0.1, 0.03, and it seems to end around here, 0.004, because of course it can no longer perfectly hit the points. Before, the error could get down to essentially 0, 10 to the minus 5. Now it can't get any lower than this. So it does the best fit it can. And again, it's pretty good, 1.99 and minus 0.99. It's very close to 2 and -1. So it worked pretty well. That's learning with errors. And here you've got a flag you can turn into the scoreboard. You'll just find this word on your screen, and whatever's hidden behind the green bar is what you type in as the answer to get in the scoring engine. And now, if we try to fit something that is not a straight line at all, then it's going to fail, of course. If this is a parabola, x squared minus 4x minus 5. So it can't really put a straight line through that, and I'm only using one neuron, so it only has the ability, it only has 2 parameters, slope and intercept. So logically, it's going to have pretty high error even when it draws the best line it can through data that is really not a line. So it starts with an error of 13, and it gets down to an error of 4, and it pretty much can't get any better than an error of 4. And so it's going to get numbers that don't make any sense, minus 0.77 and minus 5, as it tries to put a line through something that's not a line. Anyway, let's move on to making a more complex curve fit here. So there's a bit longer code. And I'm going to make a new notebook for this. Doesn't really have to be, but it's just sort of clean. I move this one to the trash and return to Colab and make a new notebook. And then put this stuff in. Okay. And what this is going to do is make a much more complicated model. Instead of just one neuron, it's going to have one neuron for X to come in, and then 64 neurons to do processing. That's called a hidden layer, and another hidden layer of 64, and then one neuron in the output. So it's got a lot, and this one neuron feeds into all 64 of those. Each one of these 64 feeds into each one of those in the second layer, 64, and then they all combine down to 1 here. So there's a lot more parameters, as we're going to see. So when you run it, it's going to print out the parameters, the shape of the model first. When it gets ready. Import, there we are. So here's the model. One neuron at the start to take X, that's got 2 parameters, slope and intercept. Then 64, which is 128 parameters, because each one of those 64 has a weight, a slope and intercept. Then this one is going to have 64 squared times 2, something like that, 4,160 more parameters. and 65 parameters on the output. So now, before we only had two parameters, slope and intercept, now we have 4,355 parameters. So it's working in that complex of a space, but it still is able to do a partial derivative on all those parameters and figure out what direction will make the error go down. And you see it works. The loss is 0.2, the loss is 0.19, 0.18. And so it goes down. After it makes a bunch of steps, you see it ends up with a pretty good fit for this curve. And this curve is x times cosine x plus noise. So it did a pretty good job fitting that. And now you can play some games with it. We can try having fewer layers. So let's try removing one of the intermediate layers. If we go back here and we just remove one of the hidden layers by putting a pound there, now it's going to have one input, 64 neurons in a hidden layer, and one output, only one stage of intermediate processing, so many fewer parameters, and it will therefore probably do an inferior job of fitting, you would think. So this is now only 195 parameters instead of 4,000 and more. Let's see how well it did. And you see, did pretty terrible. You had a really rough approximation of following that curve, but it wasn't very successful at all. And so you can try various ones here with different numbers of units per layer, different numbers of hidden layers, and see how they do. And all right. And you can try adding different amounts of noise and different amounts of data. I was surprised. It took a lot of data points for this to work. When I took it down to just like 20 or 30 data points, it didn't seem to converge very well at all. So it's interesting to see, and that's curve fitting, which is essentially all any of these models are going to do. That's why if you understand this simple task, that's really all any of these models are going to do. We'll see all the bells and whistles they add, but they're all relatively minor variations of this simple task. So I'm going to stop this one.